I'm going to walk you through the basics of solving absolute value functions, and graphing them on here a little bit. It's not a long lesson. It's not a particularly long lesson. Once I finish, if I have time, I would like to go into Delta Math and do a problem or two in Delta Math so that you can see how they work in the system that you're going to be solving them in. Just so you kind of have a good idea of both. Like how do I do this on paper? What does this look like on paper? And then, well, how does that translate over to Delta Math and how we enter things into Delta Math? Um, so absolute functions, absolute value functions, absolute. I need to up the sensitivity on this tablet so that it writes when I write. Absolute value functions um, are written as f of x or g of x or h of x or whatever, right? Whatever we're naming that function, and we're saying it is the absolute value of x. Now, there's sometimes it's not just going to be the absolute value of x. That might not be the only thing inside your absolute value lines. Like you could have x minus 4 or 4 times the absolute value of x, or you can have the absolute value of x and then plus 4 on the outside. And what that does is it moves these values around the graph differently. But if you have a table, it won't be too confusing. So if I have a table, say I have a table that's like x, right? And then f of x, which in this case is just what the absolute value of x, right? Because that equals f of x. If I plugged in -3 into the absolute value, remember, absolute values are always positive, right? Because we're talking about a distance from 0. If I have -3 in there, it's still only a distance of 3 from 0. If I plugged in -2, I would get 2. If I plugged in -1, I'd get 1. If I plugged in 0, well, 0 is still just 0, right? And all I'm doing is I'm taking whatever this x value is that I'm inputting and I'm putting it into this absolute value right here and seeing what comes out. Now, like I said in the beginning, it's pretty easy, right? It's just the absolute value of x. Whatever the negative is, just gives us the same thing in a positive because it's just that distance from 0. And I'm not going to reteach that whole part of the lesson because we did that last semester. If I put in 1, I'd just get 1 out because 1 is a 1 unit away from 0. 2 is 2 units away from 0. And you kind of get the picture on that, right? When we graph them, let's see, hopefully it's still here. Oops. I think I have it under quick access. Yes. So if I want to graph this absolute value function, all I'd have to do is plot each one of the points. And let's do it in another color so it stands out a little bit. We'll go with, so if I have -3, my x is -3, right? I have a point right there. I have a point right here. I have a point right here. I have a point right here. And then when I move into the positives, it's the same, right? My 1 brings 1, my 2 brings 2, my 3 brings 3. And I could do this all day. When we graph these, they graph like a letter V. Absolute values graph like a letter V. So in like quadratics and some things, you'll see curves. Absolute values are never curves. They're always like sharp V-like graphs. And what they also are is symmetric. And what that means is what's happening on one side of what we call the vertex, that turning point, that bottom of the V, is always going to be happening uh, on the opposite side of the V, right? Like if you notice, as we move up this y-axis, which happens to be our vertex point, one away at one away at one, two away at two, two away at two. It's always going to follow that symmetry. Even if we start further down, whatever that vertex is, every point will have a point the same distance away of what we call the axis of symmetry, which is that middle ground. Absolute values are always symmetric. Let's see. So the vertex is that turning point. Little bit of vocabulary, right? Vertex is the turning point. So at this point, our vertex would be 0, 0, right? Because that's where that point is where it turns, right? It would be right there for us in this one. So our vertex would be 0, 0. And this is your basic, like this is the most basic, we'd call this the parent function of absolute value, where we just have the absolute value of x itself. And if it was that easy, then it would never change, right? It'd always just be the absolute value of x. But we, of course, have to screw with that a little bit. And what I mean by that is we're going to start moving x around. So we're going to do some rules. We're going to do a set of rules. I was wondering if there's like a text box on this thing. So I was hoping I could put in like some actual text that I didn't have to write. See anything that's got a... I know there's a way to do text on this, but apparently maybe on the formula editor. Nope. All right. You just have to deal with my bad handwriting for right now. So steps to graphing using tables, to graphing. Absolute value. Number one. Ah, man, what happened there? My video is going to be so bad. It's going to be like me shrinking the screen because my hand happened to touch the tablet, which it should be able to do without shrinking the screen. So steps to graphing absolute value. The first thing that you want to do is find the x value of your vertex. God, having a day. Find x value of the vertex. That means we're trying to find that turning point. And the best reason I can give you for doing that is it gives you ideas of what to input for table points. right? If we know that center, we can pick points that are around that center on both sides of it when we're looking for points to plot. So and then we want to, I'll show you how to do that. I'm not going to write down how to do it. We're going to take that x value and we're going to put value in the middle row of your table. And then you're going to fill out the table around it. And graph. So let's just get to doing it because I think it's always easier to see. I brought up a text box there on accident. I couldn't do it on purpose, but I did it on accident. So let's look at a problem. I am going to do an example. F of x equals the absolute value of x minus 4. Now, one of the keys is to make sure that your absolute value is the only thing there, like there's not a bunch of add-ons with it. When we want to find that x value, that first step says find the x value of the vertex. And the way we do that is just by taking this absolute value, the inside of it, and setting it equal to 0. So x minus 4 equals 0. And then we would add 4 to both sides, right, to get x equals 4. And so that middle point of our graph is going to be 4. That vertex is going to be at x equals 4. And so it says put the value in the middle row of your table. At least that's what it's supposed to say, but I forgot the words in the. So here we have our x, and here we have our absolute value of x minus 4, or you might see it written as f of x when you put it there, where that just means that you're taking that value and setting it equal to whatever it is. And so if I know that 4 is my middle value, I'm going to have like 3, 2, 1 here, and 5, 6, 7 here, right? And we're going to just put numbers around it because what this 4 tells me is this is the middle point. So I don't want to start from 0 because 0 is too far away. I don't want to put in negative numbers because negative numbers are too far away. And your graph is going to have to be enormous to fit all those numbers, which is why we always find that x value because it gives us this starting point that we can build from. So I can do all the math on these, but we can kind of just do it. This is a fairly simple problem, so we could do it in our head, right? We have this absolute value of x minus 4, right? If I plug in 1 for x minus to this x minus 4, that's saying 1 minus 4. Well, 1 minus 4 is negative 3, right? If I plug in 1 minus 4 into the absolute value, I get the absolute value of negative 3, which we know is just 3. If I did the same thing with 2, 2 minus 4, and I took the absolute value, I'd get negative 2, which is just 2. And you can kind of see how this plays out now, right? If I did it with 3, 3 minus 4 is negative 1. The absolute value of negative 1 is just 1. 0, well, I'm not plugging in 0. If I plug in 4, 4 minus 4 is 0, and the absolute value of 0 is 0. 5 minus 4 is 1. 6 minus 4 is 2. 7 minus 4 is 3. And you can see the symmetry, right? You could see that 3 away from the top is 3, right? Here's our middle. And if I go up 1, I get a 1. If I go up 2, I get a 2. If I go up 3, I get a 3. And those are my distances, right? And they are symmetric. You're always going to have that where it kind of comes back. Your Y values start to come back. Your X values might not come back in the positive or negative direction, but your Y values will always be the same at that turning point. So if I'd have just done all the way like 1 through 4, I would have been able to fill in 5, 6, 7 without even looking at the numbers, right? I would just know that they had to be symmetric. And so when we go to graph this, right, we filled out the graph and now it just says we got to graph it, and we can do that. So here, when I go to do my graph, I've got a point at 1, 3. I have a point at 2, 2. I have a point at 3, 1. I have a point at 4, 0. And then I can kind of come up doing the same thing. Maybe if I actually turn the pen back on after turning it off again. And then we just make our V. Now these go on for infinity, so you can just put little arrows at the end, and they're all gonna kind of work out that way, right? Let's see if I've got one that. So what you could see is when we added something inside that absolute value, when we did something with the x, when we're doing something to that x value on the inside of the absolute value, it's going to shift left or right. Our graph is going to shift left or right. Sometimes, though, we won't be adding to the inside of the absolute value. We'll be adding to the outside of the absolute value. And I want you to kind of see what that looks like as well. Um, I have a good sample problem on this one. I kind of do, but I would have preferred something else. But we'll go with what we've got, and then hopefully we'll be able to find a good one on Delta Math, depending on the time, right? Because we don't have a ton of time. So if I have f of x equals the absolute value of x plus 5, right? The first thing I want to do is I want to set what's inside the absolute value equal to 0 so we can find that x, right? And if I do that, it's just x equals 0 in this case. And so that turning point is on the y-axis, right? We're not moving this thing left or right at all. And so when we go to fill out the graph, that is the most unstraight line ever drawn in the history of unstraight lines. Let's try that a little better. It doesn't even have to be that straight for the table, but so this is where we're going to put whatever we're inputting for x, and here we're going to have the absolute value of x plus 5. And we know that that middle piece is 0, right? We know our vertex, that turning point, is 0. So we're going to put that in the middle. And then we're going to go with, say, -1, -2. Let's go to -3. And here we'll go 1, 2, and 3. So if I were to plug in 0 into this function right here for x, that would be the absolute value of 0. Well, the absolute value of 0 is just 0, and 0 plus 5. So if I wrote that as the absolute value of 0 plus 5, that's the same as saying 0 plus 5, which just equals 5. So we know when it's 0, we've got 5. If I did that for -1 plus 5, that would be +1. The absolute value of -1 is 1. So this would be 1 plus 5, which is 6. And then you'd go 2 plus 5. We can figure that out. That's going to be 7. That's going to be 8, right? Now think about this. If I go and put in 1, 2, and 3, if I have the absolute value of 1, the absolute value of 1 is just 1, right? So it's still 1 plus 5. And if you remember, I said this is symmetric. So when I did this 1 and this is 6, you can guess that next one's going to be 7 and the next one's going to be 8. And you can plug them all in and do them. But once you've seen what's going on at the turning point, the opposite's going on under the turning point, right? So as long as we know that turning point, we kind of know all our y values just by solving half of them. And then we can go and graph this. Heck, we can graph it on, whoops, sorry. We can bring in a new graph because I can't make that work for myself. So when I look at this graph and I plot the points on it, and I have this point at -3, 8, I have a point at -2, 7, I have a point at, sorry, I had a point at -2, 7, but I somehow turned my pen off. -2, 7. God. Like, I think there's something going on where, like, when I press down, it -1, I have a point at 6, and at 0, I have a point at 5. And then it starts coming back up the other side, right? And I've plotted those points. And you could see that this is this V that I can connect, and it's going to go on forever. And pretend I drew those lines straight. So notice when we changed something on the outside of the absolute value, it changed the up and down part of the graph, as opposed to when we changed something inside the absolute value, it changes the left and right. So what happens is when you're inside that absolute value, the changes on x, which is why it's going to change left to right, because our x value determines where we are left and right. When it happens on the outside of the absolute value, it's going to change your up and down because that change is happening to your overall y value. So you can kind of tell how your graphs are going to move uh, just by looking at them. Another thing, and this is the last thing I'm going to show you, and I'm not even going to really do um, a full graph for it. If I have negative absolute value of x, that's still the absolute value of x, only it's going in that negative direction, and it would graph like that. Now, it would be more accurate than that, we'd use straight lines and stuff, but that's kinda how it would look is anytime you have a negative in front of that absolute value, it's just gonna flip it, and it's gonna be under that, uh, that x-axis. And by plugging the numbers in, you will see that because 'cause you'll get points, and you'll just graph out the points. But I just wanted you to understand how that negative applies. It just flips that whole graph underneath the line. Um, I don't really have time to jump into more because we only have 2 more minutes in this class. So I'm gonna end the video here. Um, but if I go further in my class on tomorrow, I'll post that video into the Google Classroom and take this one out, just so that you have the opportunity to see more examples. And then if that doesn't work out and I don't get any further, I'll just post some other samples I'll just do some Delta Math samples for you guys and make a little video, like a 10-minute video solving a couple of problems.